As I mentioned in the introduction, this week we'll be talking about the impulse momentum theorem and Newton's second law and how those things relate to each other. What we mean by a change in momentum can either be a change in magnitude, length, as shown here, or a change in direction, also as shown here, or both. The vector delta p represents the change in momentum. And we can look at this in a number of different contexts to see what the change might actually be. So this picture here on the right shows an object traveling from point A to point B to point C to point D and back to point A. You will notice that if you applied the distance formula to all four of these points, you would have the same magnitude of momentum, although the direction is continuously changing. At point A, the direction is in the positive y direction. At point B, the direction is in the negative x direction. At point C, the direction is negative y. And at point D, the direction is positive x. So if we were going to describe the change between A and C, we would say that's a difference of 0 in the x direction and 0 in the z direction, and a difference of negative 12 because we go from positive 6 to negative 6 in the y direction. And the diagram down here shows a change both in magnitude and direction of the vector p as we go from B to C along this parabolic path. Some key ideas that are going to be introduced in this chapter, the first of which is the idea of a system. And we can consider a system to be one or more objects. Everything that is not part of the system is part of the surroundings. So, the momentum of the system can only be changed by an interaction with the surroundings. Force is a quantitative measure of interaction, so it is, in a very real sense, the cause of the change. As I hope you will recall from last week, force is a vector. It has both a magnitude and direction, and the change in the momentum of the system is going to be parallel to the force that causes that change. The change in momentum of a system is equal to the net impulse applied, which involves the total force as well as the time interval. So a force acting for a time changes momentum. And, as you may expect, since it's the point, we can predict the motion of an object by updating its momentum and its position. The six coordinates of position and the six coordinates of position and momentum enable us to describe the motion of an object and predict its future. Any number of pieces can be considered a system, and the motion of individual parts of a system can be changed due to internal forces, but the net momentum can only change if you have an external force. And this is called the principle of conservation of momentum. It is one of the key aspects of physics overall. The principle of conservation of momentum has been responsible for a tremendous amount of development over time. An interaction with the surroundings can change the momentum of the total system. Newton defined force as the agent of change of momentum. That is not the way that we normally think about forces. We normally think about forces as two objects pushing on each other, or two objects pulling each other and interacting in some direct fashion. But Newton came to this almost immediately. It's in the very first chapter of the Principia, which was sort of the physics book that Newton wrote. And it actually looks remarkably like what it is, which is a physics book. However, in modern times, we've abandoned putting this thing first and have buried it somewhat deeper into the text. Our text is a little bit different, addressing it this early in the course, and I like that. It gives us Newton's second law of motion in the way that Newton himself formulated the second law, which is that force is the rate of change of momentum. This F is delta P over delta T, which gives us an average force exerted over time. And we can also look at this as an instantaneous rate of change. And that's all we're going to say about that right now, although we can come back to this and address some interesting questions that this arises about how we're actually going to interpret forces. But for the moment, we'll concern ourselves mostly, or only, with the relationship between forces acting over time intervals causing changes in momentum. Impulse is defined as a change in momentum. It can be a change in magnitude or a change in direction, but either way we refer to it as impulse. The relationship between impulse and momentum is called the impulse-momentum theorem, and it is a fundamental principle in the way that physics is done. We define impulse directly, as you would suggest from the previous slide. It is the result of a force acting for a duration. Force times duration gives you impulse. Equal forces acting for equal times produce the same change in momentum. I think you will be surprised at the amount of physics that can be done with this very simple concept. The rest of this chapter really and truly only deals with applications of these basic concepts in momentum and impulse.